Goggles on. A cool demonstration of the power of the surface area aspect of Nano is the combustion of lycopodium powder. What makes it special is the extremely small size of each spore. Each one is around 33 micrometers, making the surface area to volume ratio very large, ideal for combustion. As you can see, when the powder is in clumps, it does not light at all. The real magic comes when the powder is blown into the air. This demonstration uses only a small volume of powder blown out of a squirt bottle. When blown over a candle, the results are spectacular.
This combustion of a powder can take many forms. If you've ever visited the Mill City Museum in Minneapolis, you've probably heard of the Washburn A Mill explosion. On May 2nd, 1878, a spark ignited airborne flour dust within the mill, creating an explosion that demolished the Washburn A and killed 18 workers instantly. It was only flour, but it still had the power to destroy the entire building. A similar incident occurred in 2008 at a sugar refinery in Georgia, killing 14. Sugar kills children. This demonstration is a small-scale version of these tragedies. A small amount of lycopodium powder is blown into a closed container containing a lit candle. I hope this gives you a good understanding of the power of small. In our second demonstration, we show platinum coated on aluminum oxide pellets versus a platinum square. The point of this demonstration is that the rate of the reaction depends on surface area. The more surface area, the faster the reactions. To be exact, the surface area of the platinum plate is only 25 centimeters squared. By comparison, the surface area of the pellet is 50 centimeters squared, about 600 times larger than the plate. In this reaction, we will be blowing hydrogen gas on the two different types of platinum. The platinum acts as a catalyst in the combustion of hydrogen, and so, the more platinum exposed, the faster the reaction takes place.
You guys should be seeing a little bit of an orange glow on your screen. That lets us know that the exothermic reaction is happening.
Flame on.
You might be wondering, how small is Nano? Let's take a look at some marigold flowers. If we zoom in on a single flower and then on its central disc, we will find some microscopic pollen grains. A nano-sized object could fit into the holes on these pollen grains.
A nanometer is 1/billionth of a meter. To put that in perspective, it would take 1 billion blades of grass to cover the distance from San Diego to New York.
A nanometer is smaller than the wavelength of light. So how can we see nano?
So, as we talked about, the nanoscale is smaller than the wavelength of light. So how do we see nano? One way we can do that is with microscopes like this. This is a transmission electron microscope. And here to help us explain the TEM is Dr. Li Pen.
Hello. So this is a transmission electron microscope. It works just like a light microscope, except it uses electrons instead of light. The electrons are generated at the top instead of the bottom. The electrons come down the microscope column, go through the sample, which sits right about here, and then comes all the way down to a screen at the bottom, and the screen can display images on the computer. To put a sample into the electron microscope, we put the nanoparticles onto a tiny copper grid. This tiny copper grid is 3 millimeters across. Then the nanoparticles on the grid go into the sample holder, which is here, like so. Make sure it's all the way closed. And then the entire sample holder goes into the microscope here. What you see here are gold nanoparticles, just like the ones we're going to work with together when you guys come to campus. So these are gold nanoparticles that are around 10 to 15 nanometers across. And we can zoom in so we can look at more detail. Here we have 3 gold nanoparticles, and they are all about 20 nanometers across. And we can even zoom in some more. This image here is a single gold nanoparticle. So you can see these dots and lines. Those dots and lines are direct atomic structure image of that gold nanoparticle. So we're actually able to see the atomic structure of that object using the transmission electron microscope.
Have you ever been looking at a lotus leaf and wondered why all of the water just rolls off? Well, it happens thanks to Nano.
On a regular flat surface, adhesion makes water cling to the solid surface. However, on the surface of a lotus leaf, there are billions of tiny nanostructures that jut out and keep the water from sticking. This is called the lotus effect. This jazzy diagram illustrates this effect. Observe it and learn. There are many applications of this property, like coating material to waterproof them, to prevent icing, as well as protect from corrosion and microorganism growth.
Mass-produced sprays are now marketed to people looking to achieve these properties on a material, but it is important to keep in mind that the properties these sprays lend are often only temporary, as the nanostructure which is responsible for the superhydrophobic properties is bound to be disrupted at one point. Nonetheless, they're still wicked cool to play with. Watch this clip of this paper plate we coated.
Nano rainbow. Rad.
Nano square.
Technologies such as your iPhones and your galaxies have tiny nanoparticles, have titanium dioxide nanoparticles. These bandages have silver nanoparticles in them. And these never wet, multi-surface liquid repellent treatment. They also have nanoparticles in them. As is this MacBook Pro laptop from Apple.
Ferrofluid consists of nano-sized magnetic particles that are suspended in water or some other organic compound. It's usually made with something like magnetite, hematite, or some other iron-containing compound, and it's covered in surfactant so that the particles don't stick together. This gives it unique properties. It was invented in 1963 for NASA.
This is some real ferrofluid and how it acts in a magnetic field. Notice the spikes. It's fun to play with. And this is the same stuff, but on a bigger scale, and it doesn't have the surfactant, so it clumps up, and yeah, it sticks.
There are also mechanical applications of ferrofluid. The low friction, but the maintaining magnetic properties of ferrofluid allows for minimal resistance when magnets are involved in machines, causing things to glide very easily. Also, ferrofluids can be made to act like needles at the nano level, and when they reach a certain point, they act like small jets, acting like a thruster almost, and this might be useful in the future for small satellites.
Ferrofluid also has applications in electronics. Specifically, it can be used to form a liquid seal around the spinning shafts that are in hard disks. It's placed between the shaft and the magnets that surround the shaft, creating a barrier that prevents debris from entering the hard disk that could damage the data that's stored on the disk.
Normally when you think of gold, you think of this wonderful gold metal. But this is also gold, and as you might have noticed, it is not gold, it is red. So why is this? This is because this is a solution of gold nanoparticles. Because the particles are so small, they diffract light differently, causing us to see red instead.
What seems to be the problem, Sam?
Well, Doctor, I see red people.
Now we want to talk to you about some fascinating research going on at the U. First is Professor Bullman, who is working on chemical sensing, which can be used for medical and environmental applications using carbon nanotubes. Also, there's Professor Douglas, who is currently working on synthesizing organic molecules and organic electronics. We also have Professor Hillmeyer, who is currently working on creating the next best water purification membrane by using block copolymers that have the ability to actually assemble themselves on a nanoscopic scale.
What are some future applications for nanotechnology?
Using nanoparticles in your body to make structures so that your cells can regenerate.
Flexible electronics.
Cure for cancer.
Flexible displays.
Invisibility.
I'm about to make the ill type moves.